An introduction to rational functions. You'll be able to say I can graph a simple rational function when we're done. Rational functions, we can begin the discussion by talking about inverse proportions. Now, when two things are inverse, it means when one quantity goes up, the other one goes down. For example, as the time spent working goes up, the free time goes down. There are other examples, of course. As distance from an object increases, its apparent size decreases. As distance from a constant sound increases, its apparent volume decreases. So when one goes up, the other goes down. There are many other examples that I'm sure you'll be able to find if you think about it. An inverse proportion equation looks like y equals 1 over x. Now, if we put that in a general form where we allow shift, we come up with this. Y equals a over x minus h plus k. So as we've done the entire year, when we see the factor or the term x minus h, that actually is a horizontal shift. And the plus k at the end is a vertical shift. Here's the graph of y equal 1 over x. So what do you see? Do you see that possibly there's an asymptote here? What about here? And here? And here? Well, when we zoom out a little bit, we can see that indeed it is an asymptote. That means, though, that some of the domain and range is restricted. For example, we're not going to be able to get to y equals 0 along the x-axis. We're also not going to be able to get to x equals 0 along the y-axis. So the domain and range for both is all non-zero numbers. We are not allowed to have 0 in the x or the y, and that means the equation x equals 0 and the equation y equals 0 are asymptotes, vertical and horizontal. The overall shape is called a hyperbola. Now we'll study this shape later, but for now this is a very special kind of hyperbola. It does have a kind of symmetry. It has a symmetry through the origin. So what we see is that for every x, y in one branch, and this is called a branch, and here's another branch, for every x, y in one branch, you can get to a point through the origin by simply switching the x to the opposite and the y to the opposite. So given that, let's graph this function. Now, we can do that first by looking at the vertical asymptote. We need to know where is x minus 1 equal to 0. And the answer is when x equals 1. So right now, on our graph, I'm going to draw through a dashed line at x equals 1. Now, what about the horizontal asymptote? Well, that's determined by the number at the end. Y equals 2 is the horizontal asymptote. So we'll draw that. Between those two, we should have a hyperbola. So it's going to look like this and like this. Now, to get the exact locations, we're going to have to do a table, an XY table. We should choose numbers around the asymptote. So for x, I'll choose -1, 0, 2, and 3. The reason I don't choose 1 is that at 1, it's undefined. Okay, substituting and finding the y values, this is a half, -1, 5, and 3.5. So now we'll just plot those points. -1 and a half, 0, -1. That completes this branch. It's going to come down through here like this. And 2, 5. Missed it. And 3, 3.5. And it heads off toward the asymptote. Here's an example for you to try. Pause the video. Here are my asymptotes. X equals -2 because we're setting x plus 2 equal to 0, and y equals -1, the number at the end. Now when I build my table, I'm going to build it around the number -2 So I'll choose -4, -3, -1, and 0. And the y values when you substitute are -2, -3, 1, and 0. So we'll plot those points. -4, -2, -3, -3, and -1, 1 with 0, 0. And it comes down through here. So, to summarize, the asymptotes can be found looking at the vertical asymptote is values that cause division by 0. You're making the denominator equal to 0 to find those values. And horizontally, we're going to look at the ratio of the highest degree terms plus a factor at the end. So, what happened, for example, on the last problem is we had basically something like this. And what happens to this fraction is as x grows larger and larger, the entire fraction gets closer and closer to 0. We did have a number added to the end, though, and the number that added to the end is what raised the asymptote. Okay, for this, let's use those ideas to find the asymptotes. Now, the first thing is you're going to find out what values make the denominator 3x plus 3 equal to 0. That would make 3x equal to -3, or x equals -1. So set the denominator equal to 0. To find the horizontal asymptote, now there's no number really added to the end. The number is 0. What we have to do is look at the ratio of the highest powers, 2x over 3x, and ask ourselves, what happens to this fraction as x gets really large, either to the right with positive numbers or the left with negative numbers? Well, what's going to happen is it's going to go toward the number 2/3. Whatever x is, it's going to appear on the top and the bottom. So those are going to cancel each other. Y equal 2/3 is the horizontal asymptote. So this is the same problem. Let's use those asymptotes. X equals -1. And remember, the horizontal asymptote was at 2/3. It'll be a little hard to see, but we approximate where that is. Okay, now we're going to generate a table, and of course that table is built around the number -1. So I'm going to do -3, -2, skip -1, 1, or 0, and then 1. And the y values are going to be approximately 1.2, 1.7, -1/3 or -0.3, and 0.2. We plot those points. And again, these are kind of tricky to graph. If you want to look at a great looking graph, you got to do this online with a computer. Okay, here's one for you to try. I'll show you in a moment what the asymptotes are, and then I'll leave it to you to put the rest of it in a computer or do a very detailed graph. Okay, the asymptotes are from looking at -2x minus 4 equals 0. That means -2x equals 4, or x equals -2, asymptote. And then look at the ratio of the highest powers, -3x over -2x. In the long run, that fraction is going to go toward the number 3/2. So that is 1.5 coming through a horizontal asymptote. Think about the domain and range of these. The domain is going to include everything except the vertical asymptote. The range is going to contain everything except the horizontal asymptote. So we can say that x can't be -2, because that's what you'd get if you solved x plus 2 equals 0. For the range is y can't be -1. Y can't be -1. Okay, and for the b part, once again, and this comes from our previous problem, x can't be negative 2, and y can't be 3 over 2. That's the easiest way to just take a single number out of a domain or range. So think about the procedure for graphing simple rational functions. The first thing that we do is we find the vertical asymptote. The second thing, find the horizontal asymptote. Then we build a table around the vertical asymptote. Plot the points and connect. We'll talk about this in a later video, but for now, can you say you can graph a simple rational function?